Hello everyone, myself Vishal Shinde, working as Assistant Professor at Department of Physics, KTHM College, Nasik. Today we have going to discuss MSc second year, semester 3rd, paper number 4th, that is the course of Energy Studies first. Students, in previous lecture we have to discuss the importance of solar energy. Solar energy, that's the importance, uses, advantages and disadvantages of the importance included in importance of solar energy. That's the another point we have also discussed the solar radiations and the solar radiations, and then the next point is nature of the solar radiations. In this lecture we have to cover the basic unit and dimension of heat and temperature. That's why the another one point discuss is concept of heat, and the last one point discuss with laws of thermodynamics. They have 4 laws of thermodynamics. First one, 0th law of thermodynamics, second law of thermodynamics, third and last one, third law of thermodynamics. In this point we have to cover the basic unit, definition and dimension of heat and temperature. First we have going to discuss heat. Definition: it is energy that is transferred between two bodies as a result of temperature difference is called as heat. Flows from the body of higher temperature to the body of lower temperature. Heat units, they have two units, joule or unit of heat is a two types of units, joule or calorie. 1 calorie is equal to 4.2 joules. Dimension: heat energy is equal to energy is equal to work. Work is equal to force and displacement. Force is equal to mass into acceleration. Unit of acceleration is meter per second square. The dimension of heat energy is mass raised to 1 into L raised to 1 into T square, and the displacement unit is displacement is also length, and L is L raised to 1 is equal to m raised to 1 L square and T raised to minus 2. That is the dimension of heat energy. We have going to discuss next point, temperature. First we have discussed the definition. It is measurement of hotness and coldness of any body is called as temperature. Then unit, common unit of temperature is degree Celsius and SI unit of temperature is Kelvin. Temperature in degree centigrade is equal to temperature in Kelvin minus 273. 0 degree centigrade is equal to 273 Kelvin. Dimension: temperature dimension is m raised to 0, L raised to 0, T raised to 0 and K raised to 1, or the temperature gradient is equal to change the temperature with respect to length is equal to the temperature unit is Kelvin and length unit is meter. That is equal to K upon m is equal to K into m raised to minus 1. That is the dimension of temperature gradient is m raised to 0, L raised to minus 1, T raised to 0, K raised to 1. Learning objective: concept of heat. Heat is either internal energy or enthalpy in transit depending on the temperature condition. During the process of heating, UV flows from one part of a system to another or from one system to another by virtue of only a temperature difference. Means the process of heating, energy flows from one point to another point or one system to another system, but is virtue of only a temperature difference. The process after heating has been completed in a different state of the system, that is a new value for the internal energy or enthalpy. The process of working and heating are transient activities that lead to a change of new state of energy. We have seen earlier that the work done on a system is a function of co-coordinates of a system. So, the calculation of work depend on the path of integration by which the system is brought from the initial to final state. Means we have to complete the process of heating, that is why the new value is formed. New value is formed, the internal energy or enthalpy. We have completed the heating process, that is why to form the new internal energy or enthalpy. That is why the also state is also in this process working and heating, transient activity leads to a change of new state, that is the energy. We have earlier that work done by a system is not a function of co-coordinate system. So, the calculation of work depending path of integration by which system is brought from the initial to final state. The same situation applies to the heat transferred in or out of system. The heat Q is not a function of thermodynamic co-coordinates, that is not a stable function. So, the calculation of heat depending on the path of integration. An amount of heat dQ therefore in an exact differential and not the differential of an actual function of an thermodynamic co-coordinates. Imagine two systems. A system A is thermal contact and the system B is composite system is surrounded by adiabatic walls. For system A along, U internal energy of a final state UF minus internal energy of initial state UI is equal to Q plus W, means heat plus work done, and for system B along UF dash minus UI dash means final state minus initial state of system B is equal to Q dash plus W dash, means heat dash plus work done dash. Adding these two equations, UF plus U dash F minus UI plus UI dash is equal to Q plus Q dash plus W plus W dash. Since UF plus U dash F minus UI plus UI dash is the change in energy of the composite system, means final state minus initial state is the change in energy of the composite system. W plus W dash is the work done by the composite system, and it follows that Q plus Q dash is the heat transfer to the composite system. Since the composite system is surrounded by adiabatic wall, Q plus Q dash is equal to 0. That is, the Q is equal to minus Q dash. Within an adiabatic boundary, the heat lost or gained by the system A is equal to the heat gain or lost by system B. That is the concept of heat. In this point, we have to cover laws of thermodynamics. They have 4 laws of thermodynamics. First law is 0th law of thermodynamics, second is first law of thermodynamics, second law of thermodynamics, and last one, third law of thermodynamics. First we have going to discuss 0th law of thermodynamics. When hot body A through in thermal contact with cold body B, heat flows from A to B and after some time the flow stops. The bodies are then said to be in thermal contact with each other, means the hot body A in a thermal contact with cold body B. The bodies are then said to be thermal equilibrium with each A and B. If two systems A and B are in thermal equilibrium with system C, then A and B must also be in thermal equilibrium with each other. This law from the basis of thermometry. We consider two systems A and B insulated from each other, put in good thermal contact with the common system C. We consider two systems A and B from each other but in good thermal contact with the common system C. System A and B will attain thermal equilibrium with a third system C. In figure shown in figure A and B, red colors that showing that insulating portion of system A and B, and this surrounded wall is a adiabatic wall. This figure showing the zeroth law of thermodynamics. If the insulating portion is removed and system A and B are brought into thermal contact as shown in figure B, we find that there is no further change. It means that the system A and B are also in thermal equilibrium with another, is known as zeroth law of thermodynamics. Now consider with first law of thermodynamics. This is the law of conservation of energy, means first law of thermodynamics is also known as law of conservation of energy. A system contains a large number of particles will always have in equilibrium state an internal energy U. Due to momentums of the particles constitute the system and their interactions. If an amount of heat dq is supplied to the system, to change in energy is given by dq means change in energy is equal to dq is change in heat is equal to du plus dw, means change in internal energy plus change in work done. dw is a work done by the system. The amount of heat given to a system is equal to the sum of increases in the internal energy of a system and the external work done. dq is equal to internal energy du plus work done dw, where dw is the work done by the system. That is why next point we have going to discuss statement of first law of thermodynamics. The amount of heat given by a system is equal to the sum of increase in internal energy of the system and the external work done. That is why the next point is laws of conservation of energy. Energy may be neither created or nor destroyed, but it can be transferred from one form to another form. The relation equation first is mathematical expression for the first law of thermodynamics is the dq is equal to du plus dw, that is the dq and dw for the heat absorption and the work done. Suppose a gas is contained in a cylindrical vessel with a piston as shown in figure of a cross section A. The force acting on a piston due to the mean pressure P is system PA. The work done by the displacement the piston through a distance dx is P A dx is equal to P dV. This figure shows that the cross section of piston vessels. Hence, we can written equation first as dq is equal to dw plus mean pressure into dV, that is the equation number second. Now discuss with second point, second law of thermodynamics. This law is expressed in several ways, one of them being no process is possible whose sole aim is the transfer of heat from a cold to hotter body. There is another way in which this law can be expressed. From the first law we have dq is equal to du plus p dv. Dividing both sides t, dq upon t is equal to du upon t plus pt dv is equal to 1. This is the equation number 1. The specific heat Cu is a function state of and is given by Cu Cv is equal to du upon t or du is equal to Cv dt. From the equation of state of gas is equal to Pv is equal to RT, that is the P is equal to RT upon V, where R is the gas constant. Using equation first, we can written as dq upon t is equal to Cv dt upon t plus Rv upon dV is equal to d in bracket Cv ln t plus R ln V bracket complete. Since this equation right hand side and left hand side exact differential, the function of state whose differential is dq upon t is called the entropy of the system and is denoted by S. Thus, ds is equal to dq upon t. That is the law of entropy. Statement of second law of entropy: when a system goes from one state to another by absorbing heat slowly, quasi-statistically at a constant temperature is entropy increases. Last one, law of thermodynamics, is third law of thermodynamics. First we have going to discuss statement. The entropy S has a limiting value of S0 as the temperature tends to 0, means entropy S has a limiting value of S0. S0 means entropy 0 as the temperature tends to 0, means temperature is 0, that's the entropy is also 0. Entropy 0 is a independent nature of system and its numerical value is not fixed at 0 Kelvin but is convenient to take it equal to the 0. The third law of thermodynamics is known as nearest heat theorem and its base development and interpreted using statistical mechanics. The assignment of student: the temperature of 4 gram of air is rise from 0 degree to 1 degree at a constant volume. Compute the increase in its internal energy. Specific heat at a constant volume is 0.172 calorie per gram per degree centigrade and joule is equal to 4.18 joule per calorie. And second problem is, what is the change in internal energy per gram of air? If 12 gram of air is heated from 0 degree centigrade to 5 degree centigrade at a constant volume by adding 120 calorie of heat. The student assignment sent by my email ID vishalshinde@ktismcollege.ac.in. In this video, we have to cover the definition, basic unit and dimension of the heat and temperature. The another one point discuss concept of heat, and the last point we have going to discuss laws of thermodynamics. They have 4 laws of thermodynamics. First one, zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics, and last one, third law of thermodynamics. The next lecture we have to cover the types of heat transfer and conductive heat transfer by the Fourier's law.